what I kind of wanted to go over was some general rules on projectile motion. So let's just say projectile motion rules. Now, a little bit of clarification. I'm going to go ahead and say it. These are for the projectile motion problems that I have in my class. If you're not in my class, your teacher might use some other guidelines, so don't necessarily take this for granted. But a lot of times in just plain old high school physics, these are the basis for the projectile motion problems. So regardless of what the problem is, if you're given the initial velocity of the object, and the initial velocity is some speed and an angle, the first thing you want to do is you want to break it up into the x and y. You want to break it up into its component vectors, because the whole idea with projectile motion is you work with the components separately. You don't work with the overall velocity vector. Keep in mind that whenever you're doing calculations in the y direction, you use the y data. That's it. That's the whole idea of projectile motion. You separate the velocity up into the x and y. You only use the y data, the y velocity, for calculations in the y direction. Now, I'm going to explain this in just a second, but for my classes, when we're doing calculations in the x direction, there is only one calculation to do, and that's the displacement. The displacement in the x is initial velocity in the x times time. And the reason for that is because in my classes, we are doing problems in which there simply is no acceleration in the x direction. And if there's no acceleration in the x direction, the velocity in the x direction remains constant. And a lot of the calculations that we use have an acceleration term in them, and that's a zero, and so those calculations are non-existent almost. Now, in the y direction, though, we use g. Unless there's some external source of providing an acceleration, this is pretty much the case almost all the time. So x calculations, constant velocity, and the y, we always use g for any type of acceleration. Couple of other things that, regardless of the scenario, are always going to be applicable. The velocity in the y is 0 at maximum height. This is one of the few places where a velocity component is 0, and I'm going to talk about another one in just a second. A lot of kids want to say the velocity is 0 when it hits the ground, and we never consider the velocity when it hits. It's always the velocity right before it hits. And then the last thing I just kind of want to mention, and I see this a lot in my classes, and they use some of the displacement values, like the height of a building, how far it goes, the range, and they use these displacement values to form another displacement vector as the components, and that doesn't, we don't do that in projectile motion. Displacement is never broken up into x and y. Not in these problems. We might in other problems, but not in projectile motion problems. In other words, we never set up a triangle with displacement values. If you find yourself doing a problem and you're setting up a triangle with so many meters on one side and so many meters on another side, that is going to be wrong. I guess the last thing, and this is almost I don't know if it's always true, but we're always going to have some initial velocity in the x direction. One more thing, and this is true in my classes. I guess some other classes, depends upon how they're doing it, but I always have some initial velocity in the x direction to cause it to be a projectile. If you don't have a velocity in the x direction, then it's basically a free fall problem, and I treat those separately. So these are kind of the general rules with projectile motion, and regardless of the scenario, and we're going to look at these scenarios again in just a second, these always apply. So let's look at a few scenarios. Excuse me. Let's look at one case where this is pretty common, where we're like maybe kicking a football. We're given some initial velocity, we're given some angle, the ball goes from spot, and basically you kick it off the ground and it lands back on the ground. And in this situation, the displacement in the y direction is 0, meaning it begins and ends at the same elevation. A couple of things that we do in my class, I never take into account air resistance, at least in my regular physics class, and so time up is equal to time down. Not true if you're considering air resistance, but that's good for us. A couple of interesting characteristics in this situation, because time up is equal to time down. We throw the ball, we kick it off at some velocity and some initial angle, and it's going to hit the ground at some final velocity and some final angle, we'll say. The final velocity, and this is the final overall velocity. The final overall velocity is going to be the negative of the initial overall velocity. So if this is 12 meters per second, this is going to be negative 12 meters per second per se. I know a lot of times people don't like putting negative signs on vectors because that's the magnitude. I'm just kind of doing that to illustrate a point here. The angles are going to be the same. My launch angle or my initial angle is going to be the same as the angle that it hits the ground. Now, since the initial velocity in the x, since there's no acceleration in the x direction, there's no change in velocity in the x direction. With that statement, and with the final velocity is equal to the negative of the initial velocity, then we can also make the statement that my final velocity in the y direction is the negative of the initial velocity in the y direction. So if I have some positive y velocity there, I have exactly the same amount of negative y velocity. It's just in the opposite direction. All because we're taking off and we're landing at the same elevation or level ground. Another situation to consider. We are throwing it off a building, a cliff, whatever. I refer to it as we are starting high and we're ending low. And there's three ways, there's three situations I'm going to look at. There's three ways we can throw this item off the building. We can throw it up in the air. We can throw it horizontally. Or we can throw it downward. Now, if we throw it upward, my initial velocity in the y direction is going to be positive. I might also reference I have a positive throwing angle. If I throw it horizontally, my initial velocity in the y direction is 0. There is no y component, which means my initial velocity in the x direction is simply what my initial velocity is. And finally, if we throw it downward, my initial velocity in the y direction is less than 0, or it's negative. And I'm dealing with a negative angle. Just when you break it up, keep that in mind. I guess up here I should have clarified when I said it's greater than 0, what I really mean is it's a positive value with a positive angle. Other than that, one more thing to consider. In this situation, my displacement in the y direction is going to be negative, meaning if I start up here and I end up down here, my overall change in the y direction is negative. My final y position is less than my initial. And so when I'm plugging in numbers to do the calculations, excuse me, the height of the building or the cliff, I'm going to reference that as a negative value in terms of dy. So we looked at displacement as 0. We've looked at the displacement in the y direction is negative. One more small situation to look at, and it's just the opposite of what we looked at. Basically, starting low and ending up high. In this case, we are going to have a positive displacement. My end position is above my beginning position. A lot of kids find this type of problem a little bit confusing because they interpret these problems as this is a building and we're trying to throw it up onto a building, which is fine. I also see a problem of kicking a field goal. We're starting on the ground and we're going to calculate is the ball going to clear the crossbar. I also see a home run. We're hitting the ball off the ground or maybe a meter off the ground. It has to clear a fence, maybe the Green Monster in Fenway for anybody in the Bo Sox region that might be listening. Shooting a basket can be similar. Anything where we're starting lower and we're going up in the air and we're going to see if it's gone up high enough. All of these are the same situation. You're starting low and ending high. And the only difference between the starting low and the ending high, and starting high and ending low, the only difference is how you treat the displacement. If it's negative or if it's treated as positive in the calculations. That's all I really wanted to kind of go through. Not a whole lot of information, but I call it my projectile motion cheat sheet, that I want my kids to use this information when they're analyzing the problems. This is the real good information, the projectile motion rules, as it were. And let them use this information in terms of trying to understand all this stuff a little bit better. Well, I'm playing with my little things here. There you have it. That's all I have for you right now. I hope you got some value out of it.